Today we will talk about the classical local theory of semilinear problems. The problem is very similar to the linear inhomogeneous equation, except that the inhomogeneous term now can depend on the solution U in a nonlinear way even. So in general, this F is going to be mapping between two Sobolev spaces. There are many examples, many important examples of semilinear problems. For example, the first one here is called the viscous Burgers equation, which is a simple model for fluids. You can see here nonlinear wave equation. You can have any sign. Here you have some nonlinearity. Nonlinear Schrödinger equation. Of course, nonlinear Schrödinger equation does not mean that, for example, the nonlinearity must be u to the power 50. This is just one example of nonlinearity. The so-called KdV equation, which has this third order dispersive term, and it has this nonlinearity. As you can see, nonlinearities can involve derivatives. It may involve also just the solution U. And another example of a nonlinear wave equation here, which has derivative of the unknown and also some nonlinear power. This is a simple model for the Yang-Mills equation. You can even include non-local terms here. So technically speaking, this is not a PDE, but this equation can be studied by the same method. Another important example is, of course, the Navier-Stokes equation. Now, in the Navier-Stokes equation, you have a vector unknown u and a scalar unknown p. U is called the velocity field, and p is called the pressure field. We only have initial data for the velocity field, and initial data is required to satisfy this divergence-free condition. And in addition to this evolution equation that gives you the time derivative of u, we also have this constraint that says that u must be divergence-free. So you can see that even though there is no initial data for pressure, we have here 4 equations. Here you have one scalar equation, and here you have 3 equations and 4 unknowns in 3D. So of course it can be studied in any dimension. So we want to write this equation as some kind of evolution equation that can be fit into the framework that we have seen in the previous slide. So if you look at the divergence in Fourier space, it is simply the scalar multiplication by the frequency variable psi. Of course, in higher dimensions, this psi is going to be a vector. So this would be, for example, let's say this is your velocity field in the frequency space. Then first you project onto the radial direction and measure the length of the projection, and that length is multiplied by the length of psi. So that would be divergence. And divergence free means, from this we can see that divergence free means simply orthogonal to the radial variable psi. So let's define the Leray projector. The Leray projector is simply the orthogonal projection onto this space that is orthogonal to the radial direction psi. So we know that this would be the projection onto the radial direction. Multiply that by the unit vector along the radial direction. So this would be a vector now. So and on this picture, this vector. And we subtract that from u, that will give us the projection onto the space orthogonal to the radial direction. And it can also be written in this way: identity matrix minus this matrix and multiplied by u. And the Leray projection is simply the real space mirror of this projection in the Fourier space. And we can immediately see that Leray projector is bounded for any s, because in Fourier space it can only shrink the length of the vector. and it's a projection obviously, and also the image is divergence free. This is actually the orthogonal projection onto the divergence free space. And using this projector, we can actually write our Navier-Stokes equation in this way. Now there is no pressure variable, so simply the nonlinearity become this. You compute this expression, which is nonlinear, the nonlinearity, and then project onto the divergence free space. That's our nonlinearity. And you can see that this Leray projector is a non-local operator. So now the Navier-Stokes becomes, in this formulation, a non-local equation, which is not really a PDE. So this lemma says that this formulation in terms of the Leray projector is basically equivalent to the usual formulation. We can define the notion of strong HS solution just as in the case of the linear inhomogeneous equations. The lemma says that U is a strong HS solution of this formulation with the nonlinearity satisfying this condition if and only if U is a strong solution of the classical formulation with some pressure satisfying the divergence free condition. So let's look at the forward implication first. If U is divergence free, then the right hand side is divergence free. So that means the time derivative is divergence free. So if you start divergence free, then U is going to stay divergence free. So U is divergence free. We have this equation. So basically what this means is we want to find the pressure. So can we find pressure such that U nabla U minus gradient of P is equal to the Leray projector? That is the question. So let's say this V is our nonlinearity. So nonlinearity, by nonlinearity I mean U dot nabla U, or directional derivative of U along U. So let's say this V is that nonlinearity, and then the Leray projector of the nonlinearity is here, and Leray projector plus a radial vector will be equal to the original vector. And we can write that radial vector always some scalar times the psi vector. So in Fourier space, we can always write in this way. That means in real space, we can always write our vector field as the Leray projector plus the gradient of something. So in other words, it's just the Helmholtz decomposition. Any vector field can be written as divergence free part and the gradient part. And this Q is of course our Q, or minus Q is of course our pressure. So simply substituting V minus nabla Q instead of this Leray projector, we're going to get this formulation. Now in the other direction, so we have the classical formulation. Now what we want to show is we want to show that this combination is the negative of the Leray projector of this nonlinearity. Okay, since U is divergence free, the time derivative of U is divergence free, and also the Laplacian is divergence free. That means since these two are divergence free, that combination will be divergence free. So this combination here is divergence free. And if you look at the Fourier transform of this combination, we see that that is one radial vector minus the nonlinearity. And this is a vector that is orthogonal to the radial direction because it's divergence free. So that means this is exactly the Leray projector, or Leray projection of the nonlinearity. So by substituting the Leray projector instead of this combination, we recover that. Now this motivates us to define the mild solution. So we have the notion of strong solution. Now the mild solution would be simply treat this as the inhomogeneous term and write this equation in an integral formulation, and any solution satisfying that integral formulation would be called the mild solution. And this is our main theorem. So we're going to assume some estimate on our main differential operator. So it assumes that this estimate that we have seen before. Delta can be 0 or positive. You can see that if delta is 0, this is simply the usual estimate for strongly hyperbolic systems or dispersive equations like Schrödinger and Airy equations. Now, if delta is strictly positive, then this is estimate that we have for parabolic equations. In particular, if h is equal to q minus 1, that is Petrovsky parabolic case. And for general h positive, this is called Shilov parabolic case. And for the nonlinearity, we're going to assume that the nonlinearity is sending the Sobolev space Hs into Sobolev space Hs minus sigma. And we assume that the nonlinearity is locally Lipschitz, with sigma equal to 0 for the non-dissipative case. So it includes dispersive and strongly hyperbolic equations. So that means that in the right-hand side, we can't have any derivatives in the non-dissipative case. And we assume that sigma is strictly smaller than h for the parabolic case. So for example, for the second order parabolic equations, h will be 2, and if you assume that the nonlinearity involves only integer number of derivatives, integer order derivatives, then sigma can only be 1. So we can actually afford one derivative in the right hand side of second order parabolic equations in the nonlinearity. And now the statement of the theorem. First, this is a local existence and uniqueness result. So the initial data is given from some ball of radius r in the Sobolev space Hs, and there exists a time interval, strictly positive, in which there is a unique solution. And this time interval, the length of t, depends on r, meaning that it depends on the Sobolev norm of the initial condition. So you can see that this capital T can be taken as a non-increasing function of r. So if you give large initial data, this capital T will tend to become smaller in general. The second part of the theorem says that this mapping that sends the initial data into the solution is Lipschitz. The third part, you can say it's the criterion on global solution. So for any given initial data, there exists a maximal time of existence, t, that can be infinity, and the unique solution on that interval. Note that the right-hand side is open. Before this was closed. Moreover, if the maximal time of existence is not infinity, then it is necessary that the Sobolev Hs norm of the solution will blow up as the time approaches capital T. Now, the proof of this theorem is similar to the proof for the ODE case. So we're going to simply sketch the proof. The condition for the mild solution is written here. Here we have the linear propagator, and here we have the inhomogeneous term. Except that, of course, now the inhomogeneous term depends on our solution U. Our mild solution must satisfy this equation by definition. So let's call that U0t because it's fixed. The second part, the inhomogeneous part, let's call it operator capital N applied to U. That means we want to solve this equation, this fixed point equation. You give U, produce that, and that must be equal to U itself. We want to look at this fixed point equation in this space. So it's a continuous function from the closed interval 0t into some closed ball in the Sobolev space Hs. Let's look at the dissipative case only, because this is a bit more complicated case, because we can actually lose derivative here. Okay, first of all, we want to show that the right-hand side here is in this space for appropriate choices of capital T and R. we start immediately by estimating the right hand side. We have this straightforward estimate that we proved before. Since G is already given and C we cannot control, capital R should be strictly bigger than this. And of course T is something to be chosen, so we think of capital T as normally very small. Okay, now in the second term it depends on that. Let's estimate this term. Now we can use the locally Lipschitz property, estimate Fu minus F0. So if we estimate that, we get F0 plus the Lipschitz constant times the norm of U. Another thing to note here is that this term can be made arbitrarily small because sigma is strictly smaller than h. So that means for any given capital R strictly bigger than, let's say, C times the norm of G, we can always choose capital T small enough to make the whole right hand side smaller than capital R. The next thing that we want to show is, of course, that this operator in the right hand side is a contraction. Then we're going to get existence. So look at the difference between these two. Of course, U0 is everywhere. That means we only need to look at NV minus NU. And that difference will be bounded by that. This is the estimate that we proved last time. And in turn, we're going to use now locally Lipschitz property of F. And that gives us the bound in terms of U minus V. So you can see that, again, here we have something small, or can be made small by choosing capital T small. So it can be made contraction. So the result is basically that given G, we pick capital R strictly bigger than C times that norm, and then make capital T sufficiently small to make this operator invariant and contraction in this space. And we're going to have a unique solution in that space. And the rest of the proof is exactly analogous to the proof of the Picard-Lindelof theorem for ODEs. For non-dissipative case, it's actually much easier. We're going to have here just t to the power 1 instead of 1 minus sigma over h. Now we have an abstract local existence result. So in order to apply this result to the concrete equations, what do we need? For the concrete equations, we have, for example, the nonlinearity u squared, u times nabla u. For the Navier-Stokes case, we have the Leray projector applied to u times nabla u, and so on. So it is important to now look at the operation that multiplies two functions together. So it's a product operation. And this theorem is our main theorem on pointwise products in Sobolev spaces. So let's say S is strictly bigger than n over 2. Then Hs is continuously embedded into the bounded continuous functions in Rn. And the Hs norm of the product uv is bounded by some constant times the product of the Hs norms. In other words, it's saying that the Sobolev space Hs is a Hilbert algebra if S is strictly bigger than n over 2. Okay, a proof. First, let's look at this. We can always assume that the functions are smooth and compactly supported. Then we use a density argument. So first, you write u in terms of its Fourier transform. We're going to get some constant, and there's going to be e to the power and so on. But when we bound it, all will disappear, and it says that the maximum is bounded by the L1 norm of the Fourier transform. Then we write here negative power of psi and positive power of psi. And we use Cauchy-Schwarz. So this part here gives us just Hs norm squared, and integration of the other part here, we get xi minus 2s, which is integrable if 2s is strictly bigger than n. So that's exactly this condition here. So in that case, we're going to get Hs continuously embedded into the continuous functions. To prove the other main inequality here, we first prove this elementary inequality. So note that this the so-called Japanese bracket is equal to 1 plus psi squared 1 over 2. Simply by using triangle inequality we get this. So here we are just writing psi equal to psi minus eta plus eta, and using triangle inequality. Try to put those two out. We get 2 to the power a in front. A is some positive parameter here. And we get 1 plus psi minus eta squared and 1 plus eta squared. At this point, we use some sort of generalized triangle inequality here to bound it 1 plus c minus eta squared to the power a and 1 plus eta squared to the power a. And that gives us this sort of generalized triangle inequality for the Japanese bracket to the power s. So we can, whenever we have just psi to the power s, we can bound it by psi minus eta to the power s and eta to the power s. So now let's look at the Fourier transform of the product multiplied by the correct weight function for the HS space. And the Fourier transform of the product is a convolution in the Fourier space. So this can be bounded by this integral here. Then we use our inequality. So we have these two parts. And the first part, you see that you can write it as convolution between the Japanese bracket times u hat and v hat. So that function and v hat. And the second one, we get the convolution between the Japanese bracket times v hat and u hat. So u hat is separate and Japanese bracket times v hat is here. Now we can use the Hausdorff-Young inequality. So imagine that you are measuring the L2 norm of the left hand side. So that will become the HS norm immediately. And on the right hand side we get L2 norm of that. That will give us HS norm and L1 norm of the Fourier transform of V. For the second term it is similar. We get L1 norm of U hat and L2 norm of this, which gives us HS norm. And those L1 norms, actually here we should get a hat here. And this L1 norm of the Fourier transforms are bounded by HS norms, as we just have seen. So that gives us our inequality. So by using this, we can immediately prove this corollary. The following problems are locally well posed in HS with S strictly bigger than n over 2. The first three equations are straightforward. Here we get u squared. That means u times u. So by the theorem just be proved on the algebra property of HS, this would be continuous and Lipschitz, locally Lipschitz. And similarly, these powers are all locally Lipschitz. So these three problems are locally well posed in HS. The fourth problem is the Navier-Stokes equation. Now, for this problem, we need to write the nonlinearity in a slightly different way. So let's compute the kth component of the nonlinearity first. So it is simply directional derivative along u. So we get u1 d1 plus and so on, u and dn applied to the kth component of our vector field. Now let's compute this divergence. So u tensor u is a matrix. It's also called outer product. And the divergence of that applied, let's say, column wise, is going to give us a vector. So that is to say, we get ui uk, that's a matrix with two indices. Then we take a derivative with respect to xi and sum over I. And if we use the product rule, we get first derivative falling on ui and derivative falling on uk. And if we have divergence-free vector field, then this part is 0. So we get simply that derivative falling on uk, which is actually exactly same as that. So that means for the Navier-Stokes equation, because U is divergence free, the nonlinearity can be written in this way. So the Leray projector applied to the divergence of this U tensor U. And this is important because in the original formulation, you see that if U is in HS, then the derivative of U will be in HS minus 1, and you have to multiply with some function. So that means this would have required S bigger than n over 2 plus 1. But in this formulation, we multiply first before taking derivative. So HS bigger, S bigger than n over 2 is enough. So the nonlinearity is now sending HS into HS minus 1, which means sigma is equal to 1. So we are losing one derivative in the Navier-Stokes equation, but H is equal to 2. It's a second order parabolic equation. So that means the Navier-Stokes equation is locally well posed. So in other words, any given initial data in HS, there is some time capital T in which there is a unique solution. Now let's look at this nonlinear wave equation that has derivative nonlinearities. Now at first sight it might seem like the nonlinear wave equation cannot support derivative nonlinearities because it's a hyperbolic equation. We can't have sigma strictly bigger than 0. But we have to remember that abstract local existence theorem that we proved works in the first order formulation. That means we have to write the wave equation in the first order formulation, and remember that in the first order formulation this derivative becomes 0th order term. So that's the main thing. So we give name to the special derivatives and the time derivative. So the equation becomes like that. So that's the nonlinearity which becomes 0th order term, and time derivative of W is simply gradient of V. So that means we have well-posedness for those variables W and V. So W and V should be in HS, which means that the initial conditions, V is the time derivative, so the time derivative of U should be in HS, and U itself, because X derivatives of U should be in HS, that implies that our initial condition should actually be in HS plus 1. So we are really talking about well-posedness in this space. U in HS plus 1 and the time derivative of U in HS. For some other equations where we have, for example, for the Burgers equation and nonlinear heat equation like this, because we need to take derivative before multiplying, if we assume that S is strictly bigger than n over 2 plus 1, then this will be well posed. To conclude, usually local well posedness of semilinear evolution equations in high order Sobolev spaces is not that hard. The hard problems would be local well posedness for Sobolev spaces with low S, or global well posedness to show that the capital T is actually equal to infinity, the maximal time of existence. And also some other interesting problems, the nonlinear Schrödinger equation with derivative nonlinearities, and KdV equation, for example. The KdV equation is a dispersive equation with derivative nonlinearities. These equations are actually not covered by our abstract theorem.